all of us here, but some people may join a little bit late. That's fine. Nikos is being so kind to sharing various aspects of the model with us, including theoretical aspects of sediment management, practical consideration, and also the tools, I mean, about the RESCON, how to use it, and what are the, yesterday I could not join all the time due to my unstable internet connection, but I heard that there was very, very interesting session and discussion on the interpretation of the results, how the model responds in this or that way, and so on. That's really great. Today we are on the last day. Of course, there are many more to learn, but we may not be able to cover in this 9-hour session, but we will try our best to deliver to the best possible extent. The last day, I mean, little less than 3 hours, Nikos will be telling various aspects, which he will tell himself. And at the end, there will be a kind of closing session. But before that, there will be 10-minute time allocated for all the participants to provide the feedback. And we will also ask a couple of 2-3 participants to reflect on the overall training. It's on a voluntary basis. You may raise your hand and we'll provide opportunity to around 3 people. If no one will raise hand, I will spot some of them. And then we'll have a formal closing session. And in this way, we will conclude today. Without further ado, I would like to hand the floor to Nikos for further proceeding, please.
All right. Thank you very much, Professor Pandeyji. So without any delay, so look, I think that today what we should do is to try to run an example, but what I would like you to do is to set up this example. And we'll do this quite fast. I will be sharing my screen. We'll have a short description of the type of the hydropower plant that we'll be studying. The key variables, and please, so look in the screen, so the variables that we are using, try to type this in. What I would like you is to feel a little bit more comfortable with, you know, setting up a model, and even if not perfect, so I mean, if you miss something, please write in the chat box. We can easily resolve this. I will share also in the chat box the file that you can use for this example, but please try to start from the beginning. Let's start with, let me perhaps first share my screen. So, do you see the RESCON first page?
Yes.
Okay. Then look, I will do import the example. But you please start RESCON and do a new project. And as we discussed, so the first task is to give a basic description, so the key information for the project. Here I just have indicative some names for the project and the reservoir, country. It is Nepal, so we try to adapt this example in the conditions that we have in mountainous Nepal. And of course, here you can write in comments any comment you would like. So usually we use this if we want to separate one model run from another. So here you can use this text box in order to make anything that will help you identify easier. So for what reason you are running this model. So for me, for this example, it is important that the important parameter here is that we have a greenfield project and that the catchment area is 10,000 square kilometer, because this parameter is involved in the climate change risk assessment. In the meanwhile, what I will do is I will share in the chat box this example. If for any reason you want to start over from the beginning, so during the course of our session today, you can use also this file. I believe you can see this in the chat. It is a JSON file named PROR example. So 21.17 kilobytes. So I think that by now we should be okay with this, the first page. As said, the important parameter is to specify that it is a greenfield project and that the catchment area is 10,000 square kilometers. Then we must specify the geometry of our reservoir. So here the parameters that we have are that the initial gross storage, the pre-impoundment gross storage of our peaking runoff river reservoir or head pond, it is for pondage. It is 10 million cubic meter. It has an active storage of 5 million cubic meter. The full supply level is at 4,500 meters above sea level. So the depth of the active storage is 25 meters. So that means that the minimum operating water level is at 1,475 meters above sea level. And our dam height approximately is 80 meters. So that means that the riverbed elevation at the dam axis is at 4,420 meters above sea level. So our reservoir length is 2,002 kilometers, so 2,000 meters. And so a parameter which is actually not so important, but it might be used for trying to fit the automatic schematization to the measured storage elevation curve. It is that the riverbed width at the dam axis, it is 50 meters. So if anyone has any problem, please write in the chat box. As long as I don't see any messages, I understand that you are okay. All right. So here we see we use 6 compartments for the schematization. We can see here the plan view with the dashed line indicating the dead storage, the dark blue line indicating the average width of the active storage, and the automatically calculated storage elevation curve. Then let's go to hydrological parameters. So the mean annual flow is approximately.
Excuse me, Nicholas.
Yeah.
Can you, what are the parameters we have to enter in the geometry section? Can you repeat it once? I'm a little bit.
Can you see my?
I have downloaded and I have imported that file you have given to us in the chat box. I am working in the geometry section. Can you repeat it once so that I can enter the value?
Yeah, so the initial, please, instead of importing the file I shared, this is as a backup in case you need to use this. Please do in file and new project so that we start from the beginning. And the initial gross storage is 10 million cubic meter. The active storage is 5 million cubic meter. The full supply level is at 1,500 meters above sea level. The minimum operating water level is at 1,475 meters above sea level. The riverbed elevation at the dam site is at 4,420. meters above sea level. The reservoir length is 2,000 meters, and the riverbed width is 50 meters at the dam site.
Thank you, Nicholas. Thank you. Thank you.
All right. So the mean annual flow is close to 200 cubic meters per second. So it corresponds to 6,300 million cubic meters per year. We have an annual hydrologic variability of 0.3, a log normal distribution of annual inflows, an average temperature of 5 degrees annual temperature of air temperature of 5 degrees Celsius, and a net evaporation of 1,000 millimeters per year. So then if we want to specify the seasonal variability, please select the mean monthly flows as a method. And I believe you can see my screen. Specify these mean monthly flows in the table. First, you need to double click on every table cell, type in the number you want to give, and then press enter. So you see we have a typical monsoon starting in June, in May or June, going till September and October. And we can consider that our wet season has a duration of 6 months, and the dry season extends over the remaining 6 months. Then we do the same for the sediment yield. First, we need to specify the mean annual total sediment yield. With total sediment yield, we mean both suspended and bed load. It is 8 million tons per year. Could be also, of course, significantly higher. The bed load expressed as percent of total sediment yield is 5%. Please note here that you need to type in 5, not 0.05. So, but please type in 5. So the mean annual suspended yield and the concentration is automatically calculated. And we assume that the bulk density of sediment deposits is 1.3. Again, we need to specify the seasonal variability. This time we select the wet-dry season as a method for the description of the seasonal variability. We assume that bed load transport occurs over a period of 1 month, and that during the wet season, 95% of the mean annual sediment yield arrives at the headwaters of our reservoir. For the if you don't, theoretically, if you don't have any assessment, better assessment for the mean annual sediment yield, you can use the empirical equation in order to get a very first preliminary assessment, where in that case you would need to specify the maximum basin relief for your catchment, the ice cover as percent of the total drainage area, and if you have reservoirs upstream, an assessment of the basin trap efficiency, as well as the classification of the regional geology and socioeconomic characterization, which according to this empirical equation affects the calculated sediment yield. In that case, you would need to press to accept this calculated value that you see here in the box named computed sediment yield, 6.24 in this example, million tons per year. If you would like to use this value, by pressing accept and save, this value will be copied in the main sediment input mask. Okay, so as a trap efficiency method, we select Churchill. We assume that there are no upstream reservoirs, so we are using the local curve for the Churchill method.
Nicholas,
Yeah,
in my screen,
yeah.
I cannot select the save button in that input data, estimate of mean and annual sediment yield. It doesn't scroll also.
Sorry, you select this button, the accept and save.
Yeah, I cannot. These pop-ups, I can scroll. It doesn't.
Excuse me, sorry, I could not understand.
Nicholas, I'm unable to select the save button. One problem is that. Another problem is that I cannot scroll it.
Yeah, it has but why is all input correct in this button and you cannot click the accept and save? Okay. Look, please try to also adjust the resolution of the display settings. This might create also a problem if you have a small resolution. So the icons appear big on your screen. This could be a solution to this.
my screen is a little bit larger. It may be
Mhm.
that problem. It may be that due to that problem.
Okay. But
Uh,
perhaps so
Excuse me.
going on desktop, right click, display settings.
Yeah, yesterday I tried it. I increased the resolution. Then also then also the screen was larger.
Okay.
Excuse me.
Yeah.
Under the geometry menu and the measured storage elevation data, I could not enter the data. When I enter, it takes 0 from 0, 0, and no data is taken, accepted.
So if you write 1400, enter,
Like,
double click, then you write here 0, and then add new row. You write, for instance, 1420, enter. Again here say 10.
yeah, I did this. I added the rows and
Mhm.
entered the data, but data could not be entered. Just 0 value displayed.
Do you press enter when you type something in?
Yeah.
Okay. Can you perhaps share your screen so that we can see? So because somehow does somebody else have this problem?
I have the slight issue as well. However, if you double click on the text again after pressing enter, it seems to refresh, and then it shows you the correct value.
Could I share the screen?
Okay.
Okay.
But for the other, so in here in geometry, you see the full screen, or so this appears in the BQART. This issue. Okay, yeah.
Okay, I'm going to share, okay?
All right. No, look, I understand what you are telling, so we will
Okay.
address this point.
Okay.
Okay. But I see you have also a problem in hydrology. So
Yeah.
it was Arun Gautam.
Yeah, I have same problem in BQRT empirical equation. The screen is not rolling out, and it hangs my computer, and I have to close it. Alt delete, Control Alt delete, and I have to go task in ending task manager, and again I have to reopen the software RESCON.
Yeah.
Okay.
My problem is the same as the Ozone as.
Yeah, I just send you the screen snipping of my screen. BQART.
Okay. Look, I understand that here in this case, so this in that case, so this if you do right click on the taskbar settings and hide the taskbar settings, so this will be appeared. But in any case, so this should this should not be necessary. So we need to be able to adjust the size of this window. So thank you for this. This is a good point. So this window from BQRT must be adjustable. I agree with you.
Yeah.
Okay.
And another issue is the catchment area less than 1 kilometer square is not accepted by the program.
Sorry, how much?
Catchment area less than 1 kilometer square.
Yeah. Yeah, this is considered. So this is data validation has been inserted.
Oh. We have a
but-
dam with catchment area 0.8 kilometer square,
Mhm.
and the data is not accepted.
Yeah. Look, in that case, so generally, catchment area is very small with 0.8. This can be easily amended. So I mean, the data validation can be 0.1 or something. So what we should really avoid was that somebody enters a value 0, because in that case, so you understand that we divide many things with 0. So this was the reason for having this data validation of 1.
Yeah, this is the issue.
Yeah. So okay, this is a good point. Although of course, so a catchment area less than 1 square kilometer is quite small. But yeah, so this is something that can be easily adopted in the data validations that we have.
And what about the storage elevation value?
For this, look, so you mean this the table here?
Yeah.
To be honest, I don't know what to say on this. Look, what I do is double click, write the number 0, press enter, then double click, write 2, 3, press enter, and should be working.
Yeah, this is
So please, if you can share information on.
yeah. Can I share the screen?
Sorry, do you see my screen now?
Yeah. Could I share my screen?
Yeah. Please share screen and stop sharing.
Okay. Yeah. Now 2075. The internet doesn't work. Then this.
If you try 1500 or 1000, sorry, first of all, we're using different numbers, but if you try, so say 2065,
75.
65.
$2065.
Yeah.
65. Okay. Enter. Oh yeah.
But in any case, sorry, I do not understand. So when you go to storage elevation curve, when you do the longitudinal profile, can you perhaps change the plot that we have there?
Now it worked.
So where you select the plot that you see on the right.
Right. Yeah, this is storage elevation.
Yeah. Yeah, can you change this to longitudinal profile?
Longitudinal profile. Okay.
Okay. And can you change to plan view?
Okay.
Yeah.
Now I'm going to put here 2075, enter, and say 0.1 millimeter cube.
No, this should be now 1.3. Sorry, 0.1. Yeah, that's right.
Yeah. Oh, okay, it worked now. Then what was the issue with the 2065? I had to put this first.
Yeah, you start going from smaller to larger.
Oh, thank you. Okay.
Okay. Okay, this is a good point where we need to explain this. Okay, then we were in sediment. Let's go to economic appraisal. So please specify here the specific cost for the construction of our power plant. Sorry, let me share my screen. Okay, so let's go to economic appraisal, costs, and please specify the specific cost. So have a value of $0.93 million per megawatt. We assume that the annual operation and maintenance costs are 1.5% of CapEx. So as a range, usually this range is between 1 and 2 to 3% of CapEx. With the larger the hydropower plant, the lower the operation and maintenance costs. Then please select that at the end of when the reservoir is, the pondage is full sedimentated, siltated, so we will continue operating as a runoff river. Then we need to specify if there is a cost for the transition from storage to runoff river. We consider that our pondage is characterized as non-sustainable if it loses 95% of its initial capacity over a finite time period. Then please, let's specify, let's see what happens with abrasion. And we assume that our suspended load has 70% abrasive particles. This could be sand or even silt, can be abrasive. We don't have a desander, so therefore the trap efficiencies must be specified to be 0. So we have relatively coarse suspended load. The median grain size is more than 0.05 millimeters with a median grain size of 0.1 millimeters. Santos, yeah, Sanita, thank you very much For the explanation, Santos, with CapEx, we mean the cost for the construction of the dam, the power station, the access roads, transmission line. So generally the capital that is required for the implementation of this project. Thanks, Anita, very much. So we assume that we have extremely angular particles. We have stellite as turbine material. This would correspond to coating. And here we have Francis turbines. So we assume that the cost for the electrical and mechanical equipment corresponds to 35% of the total cost for the project, and that the parts of generating equipment that are susceptible to abrasive wear, their cost is approximately 10% of the cost for the generating equipment. So this understands to 3.5% of the total CapEx. And we assume that the worn parts, so for example, the runners or the guide vanes, if we have pelt on the buckets, the runners, and the nozzles, will be repaired 3 times before they are replaced. And between the repair events, we anticipate that we will have a gradual loss of the generating efficiency of 3%. So that means, say, our initial generating efficiency will be at 91% at design discharge. Due to abrasion, we will have a drop of 3%, which will happen gradually until the operator will decide to repair the equipment. After the repair, so the generating efficiency will return back to the initial value. So now we need to, based on this input, we see the graph where we see that, or we see the table where we see that when the reservoir trap efficiency is 100%, that means that all incoming sediment is retained in the reservoir. So we do not have impact from abrasion. But when the reservoir trap efficiency drops to 75%, we see that actually the repair cycle will be for the runners will be 4.5 years, according to Nozaki. And for the guide vanes, 2 years. And again, if the trap efficiency drops lower because of sedimentation, then we will have shorter repair cycles. So you understand that this increases the costs for caused by abrasion if we let sedimentation in our reservoir, because it reduces the trap efficiency, and as a result the amount of sediment passing through the turbine is increased. So now we will need to copy these values, or I think that they are already copied in the table outside. So this way is how we can implement the abrasion risk in the RESCON 2 analysis. So then the next step is to select the discounting parameters that we will use. So we see this here. So for the economic appraisal, please use the exponential. And by pressing parameters, here on the upper right, we need here to specify a relatively low constant discount rate. Here we use a value of 3%, which is specified here as 0.03. And this way we give value to the benefits that will extend beyond, say, 20 or 30 years. Then, in order to assess the value of the intergenerational equity that is created through the extension of the reservoir lifetime, we need to specify also a second discount rate, called this here financial discount rate. We use a value of 6%. And this value must be higher than the value of the economic discount rate. Generally, imagine that the bigger the difference between the financial and the economic discount rate, the more value we give to the future benefits, and the more increases the value of intergenerational equity that is created through sediment management. So, are we okay so far?
Yes, you can proceed.
Okay. Then we go to the revenues assessment. And first, we must specify that we have one use, which is daily peaking, hydropower. As a next step, let's try to specify our power station. We'll have a gross head of 500 meters. An installed capacity of 600 megawatts. And the capacity factor will be 50%. With capacity factor, we mean the ratio of the actual mean annual energy generation that is produced in our power plant to the energy that would be generated if the power plant would operate throughout the year at the design discharge. So here we assume that the capacity factor, it is 50%. Then we will perform daily peaking 180 days per year. So this would be the duration of the dry season. And we want to do daily peaking for 6 hours a day. Now you should, on the left side of the screen, you should see the plot that we have here, where we see that we have 10% for ecological flow, approximately 10% of the water availability goes for the peaking operation, and we have another 30% which is used for run-of-river hydropower, so non-dispatchable run-of-river hydropower generation. What we see when the storage loss exceeds 50%, what we see is that the peaking power production is affected because we don't have enough storage to provide daily regulation. Of course, the total energy is not affected, but what we cannot do is we cannot produce power, peak energy, but we can produce instead more run-of-river energy. Then we need to specify our unit rates. So we assume that the run-of-river hydroelectricity will be sold at 3 cents per kilowatt hour and the peak power at 9 cents per kilowatt hour. Point out these are only indicative values for the sake of that sample. And generally, so that sample is of course fictional. Okay, then let's try to specify an assessment of the environmental and social impacts. And here, just for the sake of an example, I have that for the no action, we expect that it's going to be non-sustainable. So, I mean, we have a storage of 10 million and the sediment inflow is 8 million. So we'll have an impact of we specify a rating of 3, which shows a moderate impact on natural habitats. We have an impact rated as a 2 for the human uses. We can expect that erosion downstream because of the sediment hungry water effect, so will affect some river banks, so which might affect human uses. And the same also for, say, for cultural assets. Then similarly, we can specify, for example, for flushing, that it will have, for the sustainable flushing, that it will have an significant impact on natural habitats if it is uncontrolled, an impact on human uses rated as 2 because of increased concentrations. And we provide also similar ratings for the other methods.
This one, no.
Okay, now let's try to specify a few sediment management alternatives to see what happens. Let's go in catchment management. And we expect that we can achieve a reduction of 20% of the suspended yield through nature-based measures and a reduction of bed load of 30%. We need to specify some respective implementation and maintenance costs. And we assume that this will be implemented from the first year of operation. and their impact will be realized within 1 year. Let's try to specify also sluicing. So we assume that we will have a water level drawdown of 25 meters down to the minimum operating water level, because yesterday we said that if we go below the minimum operating water level drawdown, we won't be able to generate during the wet season, so this will have a huge economic impact. We want to see what will happen if we perform sluicing during the wet season, so over a period of 6 months. We consider that
1.59.
so the costs for the spill, the necessary outlets are included in the design of in the CapEx, but we will have additional $1 million per year for maintenance of the, for example, hydraulic structures or for monitoring activities. Let's specify also the bypass. So let's start. We say that we will perform bypass during 5 months during monsoon. First of all, what we see on this plot on the right is that during this period of 5 months, which corresponds approximately to 40% of the hydrological year, we have close to 80% of water inflow and 80% of sediment inflow. Or in other words, when the bypass is closed, the remaining 7 months, we have 20% of the mineral flow occurring and 20% of the sediment inflow occurring when the bypass is closed. And we see this here, in this plot here. So when we press here normal operation, we see that the water corresponds to 20% of mineral flow, suspended load 20% of min-annual sediment yield, and bed load 0%, because bed load occurs during wet season when the bypass is operated.
1.2.
So then we need to specify what is the efficiency of bypass. What is the percentage of the water inflow that arrives in our reservoir when the bypass structure is open, that is diverted downstream. So we assume that 60% will be diverted downstream and 40% will enter the reservoir. Same, we need to specify the respective efficiencies for suspended load and for bed load. We assume that 80% of the suspended load will be diverted downstream and 100% of bed load will be diverted. This has to do with the arrangement of the sediment bypass inlet portal. If we have any diversion weir, what is the elevation, the geometry of our inlet to the sediment bypass. These are parameters that can be used to control the efficiency of bypass. Again, so here we haven't specified cost, but let's assume that they have a cost of $50 million. The maintenance cost is $5 million per year, and the implementation costs are, say, $50 million, because we have a relatively short reservoir. So we need to consider that the maintenance cost most likely will refer to repairs in especially in the invert of the bypass tunnel, because we can expect abrasion, concrete abrasion, due to the impact of particles, which are transported usually under supercritical flow conditions. So that means we have high flow conditions, high velocities in the bypass tunnel, with purpose, of course, to minimize the cross section of the bypass, because this is a key cost driving parameter. So that means high flow velocities, abrasive conditions, especially if we have hard particles, like it is the case in Nepal. So, and this is the key parameter that needs to be assessed in order to assess the costs for maintenance in bypass tunnels. Okay, please let me know if you're okay with the definition of bypass. Suman, to answer your question, yes, the model has been applied, and so the question, which method of sediment management is economically feasible for storage project, this is really a difficult question, which actually does not have a unique answer. So I mean, every reservoir you can see, so there are so many parameters that might affect the operation, the economic performance, the sedimentation, and the performance of sediment management, that really there is no answer that fits all. So meaning, in order to see what sediment management can be considered to be economically feasible for storage project, requires an analysis to be performed. What we can say is that catchment management is an important parameter, so to reduce the sediment yield, but it might be the case that it is not enough. So this is what I could say to this. Management method that is better suited for mountainous terrain specifically. Again, so I want to highlight that really sediment, same as you will never see the same hydropower scheme. So it is really must be tailored on the local prevailing conditions. So that's why every hydropower plant is different from another. And the same applies also to sediment management. In any case, so we can say that, for example, if we have a short reservoir, so the length is not very much, so that so bypass provides an option that can be evaluated. Same applies also for sluicing. Depends a lot on the design of the dam, the geometry of the reservoir. The reservoir geometry is an important parameter. If we have a relatively narrow reservoir, flushing is a method that can be very effective. But we need to make considerations of the environmental impacts, and we need to plan the necessary mitigation actions. The key point to both questions from my answer is that really there is no solution that fits all. So it's really important to understand the sedimentation processes in the reservoir, the economic performance of the reservoir, and so how can we have an effective sediment management strategy within what range of parameters? Because everything, so if we go too deep with the water level drawdown, we can have effective sluicing, but on the other hand, we will lose so much water that it will affect our economic performance. So that's why it's really a trade-off actually between effectiveness of sediment management, water losses, costs for implementation, and benefits that we have from conservation of reservoir storage. For example, if we conserve the reservoir storage, then most likely we won't have severe problems with abrasion. This is one consideration. So this is a very important benefit. So the moment for this, and just for the glacier lake for GLOF and landslide dam outburst flood. So this is not for disaster risk management. So this is not something that can be considered in RESCON. So with RESCON, we consider the long-term performance using annual time steps. But for events like GLOF and landslide, this cannot be considered in this model. This must be clear. The only thing that we can do is to assess what is the impact on the long term. If there is a risk for landslides, then we should consider a higher mean annual sediment yield on the long term. If we have a lower risk, then this shall be considered in the evaluation of the sediment yield that arrives.
Nicholas, I have a question like a follow-up question to that.
Mm-hmm.
So for this kind of trying to look at more extreme scenario, does it make sense to maybe run the same model considering sediment in like normal year versus sediment in a very high flow year versus sediment in low flow year? So trying to do like 3 different sediment scenarios and using that as a way to assess the cost of mitigating different classes of disaster. Do you think that's something this model could be used to do?
This could be an approach. So that, look, if you take measures against landslides or and they have a specific cost. If you expect that these measures will reduce the sediment yield in the reservoir, then you can run 2 different models, one with the increased sediment yield without the landslide protection measures, slope stabilization or nature-based solutions, and one with the reduced sediment yield, including now the costs for the landslide protection measures, and see how the reservoir behaves, both economically and the physical performance. And then see how also sediment management is affected. For me, RESCON provides an opportunity to see how the reservoir behavior is affected if we meet measures in the upstream catchment. Hope this answers some of the question.
Yeah, thanks.
And so coupling with numerical models for sediment management, no, not coupled. One thing I did so a few years ago, actually, so I compared the just out of this, so for a project actually. So I did the numerical simulations with HEC-RAS for a reservoir sedimentation and so an assessment of reservoir sedimentation with RESCON to see how they compare, and there was a good agreement. But direct coupling, no, it has not been done, at least as far as I know. We will discuss about the impact of climate change on sediment transport in a few minutes. Okay, look, now we have a few methods specified. Actually, here in the example, I have also other methods. What I would like to do is that now we go to results so that we see what is the performance. Okay, we discussed yesterday a lot about this. Let's go now to screening, where we can have a comparison of the different alternatives. We have two different options. So first is that we compare the different sediment management alternatives to the no action performance. And the second is that we compare the different alternatives to the best possible performance. So to the sediment management alternative that has the best performance. Let's start with the first one. So we have, first of all, a grouping between non-sustainable solutions and sustainable solutions. So here we see that actually, so this point here is the no action. We have a lifetime of approximately 10 years. Look, if we go to the results of lifetime, we have a lifetime of 14 years. The reason is that our trap efficiency is low and drops very fast. Okay, so after 13, 14 years, our reservoir will be extincted. Then we see that catchment management, first of all, extends the lifetime compared to the no action and has approximately 4% better performance compared to the no action scenario. So what we see here is that, first of all, we have a reduction of the sediment inflow. For this reason, we have an extension to 24 years, which is higher. But what we can see is that what we specified as an efficiency of catchment management is not enough in order to have a sustainable solution. Okay, we have an extension from 14 to 24 years of the reservoir lifetime. But so this is limited by the efficiency of catchment management measures in our upstream catchment. If we have more aggressive measures, then we could have perhaps a higher sediment yield reduction, but still there would be limitations. And we see that the economic performance is slightly better through this extension of the reservoir lifetime, which refers to active storage, than the no action. We have a difference of approximately 4%. Then we see that actually density current venting for this specific reservoir is not technically feasible or effective, so we don't see any important difference compared to no action. And now let's see what happens with the other methods. So we see that bypass here improves the economic performance. First of all, it is sustainable. So this means that it is plotted on the right graph. And that the long-term storage capacity that can be sustained through the implementation of bypass is close to 20%. So we can protect on the long term 20% of our storage capacity. Same conclusions we can see also for the other methods that I have tested here. And one thing that we see here is that actually the best performance is the combined strategy. Here, let me go back to input. Let's go to sediment management. And here, look, I have said that specified that the first year will have catchment management. And then starting from the second year, we'll have the implementation of bypass and sluicing. Again, here we need to specify the different parameters for the techniques that are involved in this strategy. And so we see that the best economic performance is achieved through the combined strategy. We see that actually with dredging, we can sustain, of course, with dredging, you have the possibility to sustain as much you want from the reservoir storage, but it is expensive. So same goes also with tracking, but still we need to consider the cost. So here what we see is a comparison of the different methods with regards to economic performance, if they are non-sustainable or sustainable. If they are non-sustainable, what is the lifetime for the non-sustainable solutions? And if the solution is sustainable, what is the long-term storage that can be achieved? So generally, the more to the up and right, the better the solution. Then the second option, I know that this looks very chaotic, but if you select only no action, this radar chart shows the performance of this sediment management strategy. We can say that no action, no sediment management is actually also a strategy. So for different aspects, functions of the reservoir. So one is the reservoir lifetime, the long-term storage, the economic performance, the value of the intergenerational equity that is created, the financial performance, and the environmental performance. And then we can compare this, for example, with the combined strategy. And we see that actually the combined strategy has the best performance if an alternative is here at the outer side of this radar chart, so that means that it is the best performance, except from the long-term storage. If we compare flushing, we see that it has also a very good performance. But so the environmental performance is not so good. So these are considerations that actually it's again difficult to say what method is the best, but this serves to provide an indication of different aspects that are affected by sediment management and shall be considered in the selection of the optimum alternative. Then we have again similar results for the storage conservation, the trap efficiency, water yield, revenues and costs for the different alternatives. Again, you can select so what to plot in the different graphs. Okay, so this is a way to compare the different alternatives within the interface of RESCON 2. What I would like to ask is, were you able to follow this example? So during typing in the information, and is it clear? So the procedure, so to specify the input, to go from input to results, to understand so why a sediment management alternative might be more effective for storage conservation, but the economic performance might not be so good. So for me, these are the key takeaways that I would like you to have from this training, and to feel comfortable to insert the parameters so during model setup. Okay, here's silence. I would suggest let us have here a short break, and then what I think that it would be we should do is go to the climate change analysis. All right, so let's have a 10 minutes break, and then we continue with the climate change analysis.
Sure, Nicholas, we'll do that.
Thank you so much.
Can you stop sharing your screen?
Give me a second.
Possible?
Yeah.
Yeah, thank you.
अनि 10 मिनट ब्रेक पास बसाली बसाली
Hello, Nicholas. Are we ready? Good to go?
Yeah, I think we are good to go.
Yeah. Okay. Thank you.
Okay. So let's discuss now about the climate change analysis. And before we start, so Ms. Sanita yesterday said that there is a portal that has been developed by EasyMod that provides a climate change data set for Nepal. And given that this is a very important input for the climate change analysis, I would like to invite Sanita to provide a short overview of the EasyMod climate change portal. Sanita, if you hear me, the floor is yours.
Yeah, thank you. I'll just share my screen.
Okay.
And run people through this. Can you see my screen now?
Yeah.
Yeah. So this is the climate data download tool inside the regional database system at EasyMod. You are required to set up a login to access any data sets that we have in the RDS. But login is free, and it's just a way for EasyMod to track how many people are using the data. So you don't need anything special to be able to download this data set. So we have compiled climate change data for Hindu Kush Himalayas, specifically in the Highware project. And then we also have other data sets for South Asia from other projects. So Highware project only looked at GCM data sets from the CMIP5 models. And then we have Cordex dataset that uses RCMs. So RCM datasets for South Asia. And then we also have CMIP6, the GCMs that are already available for CMIP6. These are models that have both precipitation and temperature dataset already. So the CMIP6 one is a very new addition, but Highware and the Cordex datasets, they've been around for some time, and yeah, should be relatively straightforward to use. For each of these projects, the domain that is available varies. So based on the project, you have the option of selecting specific subbasins that the project covered, and then for that subbasin, you can request data for precipitation or temperature, and then you can also specify which climate scenario you want. So there's RCP 4.5 and 8.5. Some of the other data sources will have other scenarios available as well. And then you can also specify what years you want the data for. So most of the data sets in this portal right now will be available for you in netcdf format. So it's a gridded data set. Once you select this download button, you can fill up this form, and then I can just do a quick run through here. Then it will tell you that the data set will be ready after some time. So depending on how many number of years you picked or how big your basin is, sometimes this takes a bit of time. But after it's ready, you will get an email where you can open the data, and the netcdf file can be opened in QGIS or also processed further in ArcGIS. So that will be a gridded file that can show you a sample of what that looks like. So this is one of the data sets that I picked randomly before, and it's already ready, so I've downloaded it. But you get a data set that looks like this, which is a big NC file. And right now I have QGIS, so I can just open it in QGIS, I think. But this is basically a gridded data set, so you can use your own project catchment areas and use your own shapefile to further use the cells that are relevant to you to calculate the delta change in precipitation and temperature yourself. So this, using the RDS data set, takes a little bit of additional effort on your end. I think the QGIS is taking a bit of time to load. But if you are working for the case of Nepal, we also have the climate change scenarios specifically for Nepal. And this is data that was also used in developing the National Adaptation Plan. You can read more about this data set in this metadata section here. So basically here you can see the ensemble of 8 GCMs that were selected for all of the Hindu Kush Himalaya region. So here you can see the ensemble mean for those 8 GCMs. And you can also download this data that is that is the change in temperature and change in precipitation calculated at each district level. These data links will again take you to the RDS page for this. Yeah, similar to before, you can just download this data. This is just an Excel file, so it's available for download right away. It's not like the bigger NC file that you get from the climate portal. So for example, for this exercise, you could easily pick up these numbers and input that as part of one of the climate scenarios. So this is temperature change, and then if we select precipitation here, you can also get the change for precipitation in the medium and long term. There is also some hydrological simulation data set available for Nepal, but it's I'm not 100% sure how much is available, but I would encourage you to explore this and see if there's any data set here that you could use right away. I wonder if the QGIS is opened. Yeah, so this is a sample of what the netcdf file looks for precipitation change from the Cordex data set. Yeah, that is all.
Okay, great. Thank you very much, Sanita. I think this is very useful. And as said, so of course it's always good to use results so that are from specifically for the country, the watershed, the project area that we have. Yesterday we saw the World Bank's climate change knowledge portal. This is also a source of information, and of course there are also other freely available data sets that you can find in internet. And Sanita, thank you very much for this very nice presentation. And I see that you have posted the respective links. So please go digging there. So let us return to the RESCON 2 analysis, and let's go to the climate change. So we discussed yesterday about the specification of the input that we need here in the tab hydrology climate change. We can specify the temperature increase and the change in precipitation in millimeters for the different GCMs. So it's possible to specify manually the impact on runoff, the hydrologic response to climate change, if this information is available. If not available, then it's possible to use an empirical equation developed by Gardner and published in 2009 for the assessment of the percent change of the mean annual runoff to different temperature and precipitation scenarios. An important input is an assessment of the increase of the hydrologic of the annual flow variability. So here you can run this either as a sensitivity analysis or if there is the respective modeling. So this can be the outcome of the this activity that should be performed before any RESCON 2 analysis. If not available, you can run different scenarios to see how the sediment management can be used as an adaptation strategy. The next point is to specify the impact of climate change on sediment yield, on sediment transport. Again, so this time we cannot click the cells of this table because these values have been specified earlier in the hydrologic input mask. What we can do is we can change, we can specify manually the impact on sediment yield. This, for example, can be accomplished through modeling with SWOT or other models that are available. And we say here that this is 5. If this information is not available, again, it is possible to have an empirical assessment with the BQ-ART equation. In that case, first we will need to specify the future conditions. For example, here we say that, okay, earlier we specified that the historic ice cover as percent of total drainage area was 15%. So now we say that it's going to be 12%. This is an empirical assessment. So this is why engineering judgment is required on this. As well as it is possible to specify if there are any indications for changes in the trap efficiency of the upstream basin that can be considered in the future development of sediment loads, or if there is a change in socioeconomic parameters of our catchment. Then after inserting this information, the next step is to press adapt the percent change, and this way, so this table is automatically filled with the assessment on percent change of mean annual sediment yield from the empirical equation. Now, earlier we saw also a plot in the hydrological information. We see one also here in the sediment specification of climate future sediment yield. So here, the different colors of the surface of the contour plot that underlies show the percent change of the mean annual sediment yield. So in that case, the deep red would be a reduction of sediment yield of 5%, and the blue color shows an increase up to 50% of the sediment yield. The different points, they indicate the global circulation models. For example, here we see the model GFDL CM3, according to which, so we have we anticipate an increase of precipitation of 98 millimeters and an increase of the temperature 2.16. And we see that according to BQART, and for this model, we can anticipate an increase in sediment yield of approximately 30%. So this color would correspond to approximately 30%. For this future precipitation and temperature conditions, we can expect an increase of temperature of 30%. So this plot shows what would be a sensible range for the response of our catchment to future climate conditions with regards to altered temperature and precipitation. So now let's go back to results. And here in every method, you see we have, so first the tab for historic climate, we have discussed extensively about these results. Now let's see what happens with climate change. So first of all, we see that here we have the different GCM scenarios, okay, which correspond to different climatic as well as runoff and sediment yield scenarios. And we see the assessment of the long-term economic performance of the reservoir for different scenarios. So this is always for the no action configuration. We see that for some scenarios we have a better economic performance. This actually most likely would correspond to a wetter future, so where we would have more water, more precipitation, and which would not be so much affected by evapotranspiration, for example. And so the lower performances correspond practically to drier futures. So this somehow describes our vulnerability of our facility if we do not implement any sediment management, which is expressed here in this plot as a percent of our baseline. With baseline, we define so the net present value for the no action scenario and the historic climate conditions. So what we can see is that for a wetter future, we could have up to 70% better economic performance, while for drier futures, we could have so up to 50% lower economic performance. The big question is that, of course, you understand we have a big uncertainty which is associated. What climate future will be realized for this? So actually, we know that the hydrologic variability will be increased, but there are many models that show that we will have a wetter future. Other models say that we will have a drier future. In order to incorporate this uncertainty in the analysis, we follow a robust decision-making procedure. This is in agreement with the guidelines that have been published a few years ago from the International Hydropower Association, as well as work that has been conducted at the University of Cincinnati with Patrick Ray. I see that Asfota Vasti is also joining. Hi, Asfota is joining the training, and she has also contributed in this work. So what we can do is we can calculate the regrets. So that is, we compare the performance now for one specific scenario for different climate futures. So let's say that no action is one of the project configurations. Sediment management or catchment management is the second configuration. and we compare the performance of this project configuration, this is the red line here, to the best performance that we have for each climate future. And this shows what actually we have to lose. So if we implement no action, if this climate future that is described by this GCM is realized, and if we would have chosen another method, sediment management method or project configuration, then we could have this performance. So this expresses a regret. This is the revenues, the benefits that we could have if we would have selected the correct or the best performing configuration for this specific climate future. This is what actually will happen if we select the no action. So you understand that we need to do this for all let's see, bypass. We need to do this for all project configurations. Again, we do the climate stress test. We see what is the performance of our project for this sediment management configuration, in that case, climate stress test. We compare to the baseline, which is no action for historic climate. We assess the respective vulnerability and the respective regrets. Here we see that actually we have less to lose compared to the no action if we select the bypass. And for this specific scenario, climate scenario, we see that it is very close to the best performing facility, best performing configuration. Now, if we go to the combined strategy and we go to the color, we see that actually the combined strategy for all climate futures, possible climate futures, is always the best performing configuration. Now, somehow we need to plot all this together. We go in the tab screening. Here we see the range of the performance of our project for different climate futures. We see that we have a wide variability. Again, we see the respective vulnerability. And here we are plotting the calculated maximum regrets. And actually, so the method that will minimize the calculated maximum regrets is the method that can provide the robust adaptation to future climate conditions. In that case, the decision is quite easy because actually the combined strategy that we have selected has always the best performance. So that means the maximum regrets for this project configuration is practically always zero. So these are the minimum. And here we see also how the other configurations are reacting. So this was a short presentation of the climate change analysis. Here, what I would like you to do is, first of all, please let me know if there are questions. Look, I would like the next 45 minutes that you will try different scenarios and let us work together if there are questions. So to try to interpret results, I would like to leave this 40-45 minutes to you, where you post questions on the chat box, if you have any, or if there are any wishes that you would like us to go more in detail during this training. If something you have the feeling that we should elaborate more. So I would like to have this 40 minutes dedicate so that you tell me what you would like more focus and more information. So I would suggest that please take next 10 or 15 minutes. So to, for example, try to specify to see how sluicing reacts, or how a combined strategy can be elaborated, so that to see what is the response of the reservoir. And of course, anytime if there are questions, please drop them in the chat box and let us discuss about this.
The coach, one curiosity here.
Mm-hmm.
In climate change scenario, I see that the temperature and precipitation are the proxy indicators which have been used. Had this model been validated in extreme climate change scenarios?
Gardner, it is a global model. I haven't checked with other models for results in, for example, in Himalayan countries. So this is a very interesting question, so which I don't have an answer for this. According to the publication from Gartner, he has tested thoroughly the model, and he says that he saw a very good agreement. But Professor, it's always an empirical model. I think so. For us, this is a first indication. We always say that actually this work must be followed by additional modeling as possible, cross-checking. This is just a first step to actually to initiate the discussion, to gain an understanding on the behavior. But it's really important to always keep in mind that we need additional modeling in following steps.
I read somewhere like in the journey from RESCON to RESCON 2, the objective was to include like climate stress test and then make the model more applicable in robust decision making. So that's why I was wondering, extreme events are extreme, so we cannot predict, and something unpredictable, and how we include in model. That was my curiosity. Sorry.
Professor, sorry, I missed perhaps the most important aspect of your question, so apologies for this. So this empirical model that we have with Gardner, this applies to mean annual values. So the externalities, so no, this is not considered. And you know better than me that actually there is really a lot of work that's going on this topic. And this is really out of the scope for this type of analysis. This is a very important topic, but we are always talking about mean annual values and not impact on extreme events. And
yeah, thank you.
so for me, do you have the feeling that the purpose of the analysis and the different steps have been explained. Look, if you don't ask me, I will continue talking. So, but really, I want to hear from you. If there is something that you would like to go more into detail, I will be happy to do so. Otherwise, there are really many methods that we can explore. So, what is how they affect the performance of the reservoir?
I have a question, Nico. So in the comparison of the different management strategies, it's pretty, I think the difference between combined and other individual strategies is quite big. Is there any good ways to use the information you get about individual strategies in these plots to create a combined strategy?
That's very good question. And for me, let's go back to input and sediment management. And look here, sediment management, combined strategy. So here actually our combined strategy is combination of bypass and sluicing. Okay, so when we go to results, sorry. We see that actually the combined strategy maximizes the economic performance.
Yeah.
We see that actually flushing has also very good economic performance. And at the same time, so extends the reservoir lifetime, the long-term storage capacity. So that means the part of the reservoir that can be protected by flushing. For me, this is an indication that actually the combined strategy should include also flushing. Of course, the number of flushing events that must be performed, the duration of flushing events, the water releases during flushing, they must be very carefully planned by experts. So in order to optimize so that you can optimize the combined the flushing operation. What I would do, I would run the different strategies one by one.
Yeah.
So catchment management, flushing, dredging. I would see what is the combination of parameters, because you see that by each method can be more effective or less effective, depending on the selected parameters. I would see what are the parameters that drive the efficiency of each method. And then based on this comparison, I would see, okay, so a combination of these methods most likely will have the best economic performance and at the same time will protect the biggest part of my reservoir, or the part of the reservoir that I need in order to have the best economic performance, without at the same time neglecting the downstream impacts. This is the way I would go forward. So go one by one the methods, see how to improve, what are the key parameters for the efficiency of each method, and then see what combination practically maximizes the economic performance and minimizes the downstream impacts.
Okay. Thank you.
Sarah, I see you have requested a remote control of the screen. Would you like to show something here on this model, or?
Me not.
Okay,
Good.
sorry. Suram, you have a question about quantity of sediment deposited and percent of flushing in normal flood as compared with respect to climate change scenario. Would you like perhaps to elaborate a little bit on the question?
Yes, sir. I want to ask about the percentage change in flossing with respect to climate change scenarios. Would you elaborate which technique would be suitable for more quantity of sediment flossings from flossing, dredging, hydrosuction, sluicing? Which parameter is most sensitive in flossing?
In flushing, the most sensitive parameters are two. The one is the water level drawdown that we can achieve through the bottom outlet in our dam. So how much we must lower the reservoir in order to achieve the free flow conditions, so to re-establish the river flow along our reservoir. And the second parameter is what is the flushing discharge, because this parameter defines also the geometry of the flushing channel. Now, these two parameters, what they do is that they define what is the maximum long-term storage capacity that can be achieved with flushing. But here we must understand that this is the maximum possible deposit removal that can be achieved, but this depends actually on the duration of flushing. If we have a small water level drawdown, then the energy slope during our flushing slope is small. That means that the transport capacity of the flushing flows is limited. We might not be able to remove within a short time period with this transport capacity all the deposits that are located within the flushing channel. In that case, what we should do would be to increase the water level drawdown to have steeper slope. So that means more tractive force, more erosion during flushing, remobilization of the deposits, so we could increase the duration of the flushing operation. So if we say we perform for 2 days, we perform flushing for 4 days. In big reservoirs, flushing might be applied for longer periods, say weeks or months, of course with the respective water losses. That's why it's very important to consider what is the operational rule of our reservoir before designing any flushing operation. To summarize, two key parameters to define the geometry that can be theoretically achieved by flushing: water level drawdown and flushing discharge. They define the geometry of the flushing channel. And then the actual deposit removal depends, of course, on the duration of flushing. If the limitation related to transport capacity of flushing flows does not facilitate the full cleaning of the area where flushing is effective.
Thank you, sir.
Okay. Okay. Perhaps in the meanwhile, look, I would like to show you, if we go again to climate change, then you see that there are also different plots. So again, based on the work from the University of Cincinnati, Patrick and Aspota, and the climate change resilience from IHA. So this is a surface plot where we see the performance for the no action configuration for different future climates. So here, the blue shows a performance close to $3.2 billion over its service lifetime, and the red shows a much lower performance for $800 million. And here again, the different white dots, they represent the different climate GCMs, the climate futures described or projected by the GCMs. This is an indication of the sensible rates of the economic response of our reservoir to different climate futures, in that case for one specific configuration. So that means for the no-action. We have, of course, similar plots for the other methods. Okay, so this provides an indication of how our reservoir will respond economically to different climate scenarios. And always we must keep in mind that this is a preliminary assessment. Here, this is fictional example. So it aims also to provide clear indications so that so we can end up to conclusions. So real life is much more complicated than the one of the examples used for trainings or to showcase how to use a model. We have similar box plots, so plots for the vulnerability. Okay, so no, we erased this, so we must remove this. So with climate change, this is the main purpose. I hope so that actually the procedure was clear, that we start by, first of all, defining the baseline. We must have something to compare what will happen in the future and for different project configurations. Then we perform the stress test, the climate stress test. For each project configuration, including no action, we see what is the response to different climate futures. We assess the vulnerability compared to the baseline. And in order to have an assessment of the project configuration that provides a robust adaptation to climate change, so we calculate the regrets, the maximum regrets. That means what we have to lose if we select a specific configuration compared to the best performance for this, for a specific climate future of the best performing configuration. So then we compare the calculated maximum regrets and we see what actually what project configuration minimize the maximum that we have to lose. So for me, it's a little bit like thinking also perhaps in poker, or say, so we have to think what can we gain, what can we lose, and then we try to find what method for a wide variety of climate futures minimizes what we have to lose. So this is the thinking behind the climate change analysis incorporated into RESCON 2. And a very important point to bring here at this point is that this is only one part of the climate change risk assessment and of adaptation to climate future conditions. This refers to long-term economic performance with considering sedimentation. Of course, you understand that there are dam safety aspects. So what happens during extreme events? Other economic aspects, other environmental aspects that must be considered during climate change risk assessment. And there is a wide variety of adaptation measures that must be included under this context. So it's important to highlight that sediment management can provide a contribution to adaptation to climate change for a facility, and that it is not the only component of an adaptation strategy. There are many different other aspects that must be considered and evaluated separately. So I hope that this is quite clear from this presentation. Okay, so look at this point, yeah. So at this point, I would suggest so that for the next 15 minutes, please go around the model, try to see how it behaves, and send me questions if you have. I made a few notes so on issues that appeared. So most important with the Mac computers that we had the problem. Then I understand that for this window, so there is no scroll down bar. Sorry for omitting this. Will be communicated to the programmers. And I guess so that the same problem should appear now that I saw this also in this window. I guess the same problem should appear because I don't see here also any scroll bar. And I understand that there was also another issue if somebody had installed the latest version of the Java development kit 11, and when we tried to install Java. So these are the notes that I have. Please, if you have encountered other problems, so I would appreciate a lot if you send me an email, so that we can address this today or yesterday. So I write in the chat box my email. So if there is something you have observed and you think could be improved, please let me know, and we will do our best to address this in the next 1 or 2 days with the programming team. So from my side, that's it for now. I would like you to, I hope that I know that you are getting also prepared for the holiday season that starts tomorrow, I understand. So if you take 10 or 15 minutes to go through the model and provide me some feedback, so or questions, I would appreciate it a lot.
Nikos, I have 2 points that could be feedback, I guess.
Yeah.
I think it was a little bit confusing to follow along as you instructed, like, you know, where to fill what, because a lot of things were already, like all of the pages already had numbers on them, even if you started with a new project. I think that is confusing. So having a blank slate might be nice, or also, or having some sort of indicator that says, you know, you filled this section or you haven't filled this section. If there's room for the programmers to add some kind of check mark or something after you've filled, like after you manually change something, then it would be easier to see what parts you changed and what parts you didn't change.
Yes, Anita, this so trust me, we made really there is a lot of thinking behind this. One thing is that we have, of course, many parameters and many interdependencies. So for this reason, so when you start a new project, that we have some key the text boxes is filled to prevent that somebody will leave something empty and will actually it's important for the stability. So if we start with an empty project, so my experience was that you need very experienced users that will understand from the beginning all the input, and actually most of the users won't have the possibility to have this 9 hours training that we had. And also my experience is that most of the users won't read the 250 pages manual. So
no, I mean, but I think this is also pretty dangerous, because you can just get, you can already get really, like, even if you don't fill in anything, if you don't change the cost parameters, for example, for catchment management versus sluice or dredging, then if you don't change the default parameters, or you only make change in one part and don't make change in another part, and then you get a result that you pass on in your design report, that's also pretty in a way. I think it's good for people to realize that the model is not running because they haven't filled it all up. But my background is in hydrological modeling, and it's very typical that in the initial setup of hydrological models, you always get a lot of error messages because there are these dependencies and you have to fill everything. It also makes you aware of the process that you're going through.
And I understand. So, and now you are right. So look at the previous version than this was with empty, and we were working with this, and look, my experience was that people would get somehow confused, and so Anita, let us think about this. So I'll tell you, I have the version ready. So with the
yeah, no, that's okay. It's just a feedback for future.
No, and I appreciate this feedback. Tell you, so we were doing really same considerations. It's somehow sometimes we try to understand what is the psychology of the user. So we don't want to discourage, and at the same time we don't want to leave the feeling that okay, so within 5 minutes I've got results. So it's somewhere in between. But thanks for the point. So, and as said, so this was really point of discussion among the team, but I will bring this up. So I will bring that we had this feedback, and in the next few weeks you will see so how it develops, but please also stay in touch in the future so for further improvement suggestions. These are good points.
Yeah, indeed. Thanks.
There are some comments in the chat box, Nicholas.
Soraya, I see sediment yield of river from catchment, debris flow phenomenon, upstream of catchment, sediment deposit upstream of dam, reservoir size, capacity inflow ratio, reservoir drawdown, sediment flushing from different techniques, cost of flushing, energy lost, environment impact. So I think you did a very good summary of the different parameters that are involved in the selection of sediment management. And I think that this is just an indication that so there are many things that we must consider during planning of sediment management. For me, the important thing is that we start making these considerations from the beginning. It's if we try to retrofit solutions in existing dams, this is very difficult and very extensive. If we try to restore lost active storage, it might be either technically not feasible or even more expensive than building a new dam. But so actually the good locations for dams in most places in the world have been constructed. So that's why it is very important that from the beginning of a project, we make considerations on sediment management so that, for example, it's important to have low-level outlets in the dams we construct. It's not, of course, dam safety is a very important aspect, but also they can be used for sediment management, and they must be adequately dimensioned in order to be suitable for both purposes, dam safety and sediment management. As far as I see the point, your comment, using different colors for default values and input could be a possible solution. Let us think about this. Sounds interesting. Thanks. The climate data that were used are incorporated in the file, this example file that I shared at the beginning of this session today. Please let me know if you have received the file. It should be at the beginning of the chat. Here, I can send it again. Suman, that was for your comment. It would be nice to paste tabular data, but this was not possible with the library that was used. But this is an important improvement that should be introduced in the tables that we have here in the interface. Krishna, regarding your comment. Subhas, your question is about calibration and validation during the setup of the model. So we discussed also yesterday about this. Look, the method actually that we have in RESCON 2 is the selection of the trap efficiency method, where we have practically 5 different possibilities. So 2 curves for Churchill curve and 3 curves for the Brun curve. They give a quite sensible range with regards to annual sedimentation and development over time. So this is the main parameter. Another parameter could be the number of compartments that will be used for the schematization of the reservoir geometry. This would have, I would say, a rather limited, so say, efficiency in calibration and affecting the calculated sedimentation, but this could be a method, and perhaps this would be more useful to see what happens with regards to the spatial distribution of sediment deposits. How is the allocation between active and inactive storage? Now, here that we have a greenfield project, so that means it's not an existing project where we might have historic measurements of the storage development based on bathymetric surveys. In here for greenfield projects, the best thing that we can do is, first of all, to have an as reliable as possible sediment yield assessment based on a sediment rating curve, which is developed from a well-designed field monitoring program. So this is monitoring is always a very important aspect for any sediment assessment. And so another possibility for greenfield projects in neighboring catchments where another reservoir has been built, and they saw there is sort of similarity between our catchment and the neighboring catchment with the existing reservoir, it would be possible to end up to some qualitative and even quantitative conclusions regarding the observed annual storage loss rate. For greenfield projects, these are the two possibilities that we have in order to calibrate the model. First, as good as possible sediment yield assessment and comparison with reservoirs in neighboring catchments. Sanita, yeah, so the description for the contour plots is given above, but this has been improved in the version that will be released the next days. Again, thanks for this. So I hope that has been addressed. Professor Pandey G, so actually from my side, I think that
It's done, right?
yeah, did more talking than I would
All
like
right.
to do, but so at the same time, so
Yeah.
we had a very nice discussion. And
Thank you.
as always, I have posted my mail in the chat box. Please, you can reach out to me through the organizers. So I will be happy to continue discussion and to provide support as you need.
Thank you so much, Nikos. We really appreciate it. Maybe you may consider stopping sharing the slide now.
Yeah.
We
Sure.
go to another phase of the program today. We had a wonderful 3-day session based on what I observed personally. Many thanks to Dr. Nikos for being with us as a resource person. Sediment management and also use of RESCON to model. We request all the participants to provide feedback on how you felt about the training with a specific focus on what we can improve in future, because the feedback means, of course, there are always areas for improvement. We want to hear from you what we can improve so that if we offer the similar training or exactly same training in the future, other participants can get the better, delivery than what we have today, because there are always the possibilities for improving better. For that, we have allocated around 5 minutes for sharing the feedback. I'll be posting a link here in the chat box. Please use your time and fill this. And if you need couple of more minutes, let us know. There are a couple of questions, very easy to answer. Most of them are kind of multiple choice questions or the option type questions. So I think there are one or two of them related to paragraph where you can express your viewpoints in the form of text. You have 5 minutes for that, then we will carry on with the remaining work. Now, Nikos, we have handed over our task to the participant, right? We are free for 5 minutes.
Great.
All right, I think it has been 5 minutes. I hope you have done it. In case someone has not finished, let us know. We can give 1 more minutes, or we are when we are having other part of the program, you can continue with filling the forms. Shall we continue? Will that be okay? Maybe okay, right? No one has opposed it. Then we can interpret as the kind of agreement. Thank you. So to continue further, now we would like to request some of the participants to share your reflections, basically focusing on what aspect you liked about the training, what do you think we need to improve, and anything else. Maybe not more than 2 minutes for one participant. We can maybe take up to 3 participants to share the reflections, preferably with the balance in gender. Anyone would like to raise the hand voluntarily, please, for sharing your reflections? No one? Okay, then let me pick out randomly. I see one Suman Shrestha. I see the one name here. Would you please mind sharing a reflection about the training? Suman Shrestha.
Yeah, thank you, Vishnu sir. I found the training was very fruitful. All the parameters that are needed for the sediment management has been incorporated, has been addressed, and what I found is the model is very easy to use, and thank you all the entire team for providing such an opportunity of sediment management training. Thank you all.
Thank you. Maybe Shanita may go next, if you are okay, for sharing your reflections. Shanita. If not, maybe
Sorry,
yes, please.
I was trying to unmute. Yeah, no, I think it's been great. It's also been the training itself was quite interesting, and I also really enjoyed the engagement from all the participants, and to hear a perspective from other people that are doing similar stuff, and also coming to realize that people are thinking about different things or having similar problems when thinking about sediment management problem. So that I think is a very different type of experience I've had in a training program like this. It's nice to learn the software, and then it's also nice to have this opportunity to share experiences.
Thank you. Any specific suggestions for future programs for improvements? That's what we want to learn from the participants, if any. No. Maybe professors. Yes, sir. Professor Sharma. Oh, yes.
Okay, I'm Shiva Saba. Okay, again, back again. And I would like to express my few words to Dr. Nikos. I would like to first thank Dr. Nikos for his time on giving a very good presentations and the training on RESCON 2. First of all, as Dr. Nikos had been saying, this is a very preliminary assessment for any sedimentation analysis. So having said that, for a pre-feasibility study, this is a very fantastic program as far as I know from a few days ago. So it is very insightful and a very detailed program, even for a pre-feasibility level. So if this kind of model is used even for a pre-feasibility, then the chances of the quality of studies will be very much acceptable, and the decisions making for the planning committees or the government would be very much helpful in order to implement the programs to take to the feasibility level or to up to the investment level. So as myself, I am also involved in the design and study of one of the storage projects, and I myself find it very much useful, and the feedback to the to the developer of this software program and to other audiences who are representing some academic institutions. My feedback to EC mode also, so maybe if we use this tool for the academics and the research institutions, then at the university level, we can find a lot of projects and we can do a lot of research in the field of sedimentation management for reservoir projects. And then if such institutions can give the thesis research topics for the storage projects, then a number of findings available even from the level of the pre-feasibility. So I find this very useful and very good, and I recommend especially to the planners and for the research students and for the graduate level students who wants to develop their career in the field of research and in the field of sedimentation management. So I'd like to thank all the team as well. And these are my feedbacks and comments combined. Thank you.
Thank you so much. We really appreciate feedback, and we are happy to learn that it was useful. We'll see what we can do in future. Thank you. I think we have taken the feedback from the 3 participants. Now we will move ahead with the session. With that, maybe I would like to invite Dr. Nikos for your final words, final reflections, if any.
So where to start? Look, first of all, thank you all for the active participation. Professor Panda, you will let me start with the participants. So for me, it's been a wonderful experience to see such an engaged team of engineers, researchers. I see Professor Sharma, so people who are interested in this topic, which if you see, so the name of the number of publications, so the last 10 or 20 years, actually, it starts increasing very much. So the topic of sediment, previous decades, perhaps I would say that was below the water surface. But so as our global fleet of reservoirs is getting older, as we understand the importance of hydropower for the clean energy transition, as we learn from things that we could improve, now talking with regards to previous designs, the topic of sedimentation and sediment management becomes increasingly important. And for me, it's really nice to see that, I mean, there is really focus on this topic. And for me, the discussions we had during this training was, and the questions and the comments that we received were really insightful and to the point. And this is the most important aspect, that, okay, we are developing technical analysis tools, we improve the understanding, but at the same time, the engineering and the research community digs in, and this can make us only optimistic for the future, so that we will have improved designs, and will reservoir sustainability will become a topic that will be considered from the beginning of any project. For me, just a big thanks to the participants. Personally, Professor Pandey, to you for organizing this event. To the team, we've been in discussions with Pratima during preparation of the event. Of course, to Pravin Karki from World Bank for supporting this training. Want also to say thanks that the development of this version of RESCON would not be possible if there was not the support from the Austrian Ministry of Finance and a big team that worked for this. So just from my side, a big thanks. So I hope that the training was as interactive as it could be. Perhaps it would be also nice to meet in person in the future. It's different that everyone types when he has a question, he raises a hand. So of course, Zoom gives huge possibilities, but raising hand is always different when you are in the same room. Just one point from my side, and these are my reflections from the training. I hope that we continue also with the second training, and that we build on the experience that we have done during the last 3 days. Again, many thanks to everyone. I believe that I have included all the important contributors.
Thank you so much. We are almost at the end of the session, and also the participants are about to graduate, I would put it in that way. So we will be distributing a certificate like this, where all the certificates are not ready today because we would like to confirm the names and print it out, get the signatures, make a digital form and put somewhere. It may take a couple of days. So certificate looks something like this. It will be a joint initiative of the Government of Nepal through National Disaster Risk Reduction and Management Authority and DRRMA, and ICIMOD as a secretariat for this knowledge hub, and CWRS, Center for Water Resources Studies with the Institute of Engineering, Tribhuvan University, who is leading this hydropower transboundary working group and designing and this kind of trainings together with ICIMOD and others. And also this is supported by the World Bank and GFDRR for developing this training and also some other supports. So the participant will get a certificate like this, certificate of participation presented to the name of the participant for successfully completing the training on managing sediment risk in hydropower projects, application of RESCON 2 model 25 to 27 September 2022, organized by Hydropower Transboundary Working Group under the KOSI Disaster Risk Reduction Knowledge of KDKS. It will be signed by the NDRRMA from the World Bank, the director, executive director of our center, CWRS, and the DG of the ICIMOD. So this will be a kind of evidence that you took the training successfully, but this will be provided only to those who actively participated in all 3 days or 9-hour session. We are taking the attendance and will be providing only to those persons. I think with this, we are almost at the end. I personally would like to thank all the helping hands who are supporting in this endeavor from the background, in addition to those who are in the forefront, like our resource person, Dr. Nikos, and all the you participants. There are several others working from the background. For example, Dr. Neeraj Vestapradhan from ICIMOD, who is leading the KOSI Basin Initiative, and she has been very instrumental in supporting it. Dr. Sunita Chaudhary from ICIMOD, she has been the focal person for this point from ICIMOD and helping a lot. Mr. Sivanga Sinha from the ICIMOD, Sharmila Dungana from ICIMOD, and Pratima Shrestha from World Bank, and Mr. Praveen Karki from the World Bank, and others. I would like to really acknowledge them for their generous support and tremendous efforts for putting all the things together. With this, I would like to now invite Dr. Arun Shrestha, Regional Program Manager for River Basins and Cryosphere Program of ICIMOD, for a closing remark. Arun, sir.
Yeah, thank you, Vishnuji. I hope you can hear me well.
Yes, sir.
Yeah, thank you for giving me this opportunity. Unfortunately, I could not join in the opening because of conflict with the scheduling, but I'm happy I could join today for the closing. And I was able to listen to some of the remarks by the participant, which was very useful. What I would like to say at the conclusion of this training program, of course, water resources, including hydropower, plays a significant role in South Asia's energy sector. But we also know that there are several environmental risks to hydropower development and its sustainability. And sediment management is one of the major issues. Sustainable hydropower development is critical for climate resilience and meeting growing energy demand in this region. So for that reason, ECMOD is working on various aspects related to hydropower sustainability. As you are aware, among others, the hydropower transboundary working group, which was set up fairly recently under the Koshi Disaster Risk Reduction Knowledge Hub, KDKH. And this working group is led by Center for Water Resources Studies at Institute of Engineering, Tribhuvan University, has organized this training to strengthen the capacity of stakeholders in Nepal and South Asia to help in understanding and managing sedimentation issues in hydropower projects. Although I could not, attend the sessions, but what I have been informed that the training focusing on a combination of lectures on theoretical concepts, case studies, and hands-on exercises was very insightful and interactive. And what I heard from participants just recently in their reflection, I think that also verified that it was very fruitful. Their comments were very positive. I understand the model encapsulates assessment appraisal of multiple parameters such as economic and environmental, enhancing is comprehensiveness, included a detailed overview of RESCON 2 and hands-on exercise to analyze sedimentation issues. And I understand it was very practical and useful. One of the participants says it was very easy to use as well, right? Which is very important when you are dealing with any new tool. I think the ease of its use is certainly an important factor. But then, taking a training is very good. I saw quite a number of participants at least until now. But the major issue is using it. So I do really hope that, the efforts made in transferring the knowledge through this training will be used in managing sedimentary issues for sustainability of hydropower projects. There was also talk of using it in academic courses for students. And I also heard about second training possibly in the future, and hopefully that could be a physical training in person. Of course, it requires certain efforts, resources, but in terms of effectiveness, maybe it will be more effective. So let's hope we can do it physically next time. With this, I've been informed that several people contributed heavily to this training. Vishnuji has already thanked, but I would also like to thank on my personal behalf, but also from ECMOD's institutional behalf, thank some of them. So the first name is Dr. Nikos Ifimia. I hope I am pronouncing your name okay, reasonably close. As you have been the resource person for this training and have spent quite a lot of energy and time in designing and conducting the training. So thanks a lot for all your efforts. Mr. Rajendra Sharma from NDRRMA for supporting this training, the corporation as a co-organizer. Participants, of course, definitely without participants, it would not be a fruitful exercise. So your enthusiasm in participating, engaging, interacting definitely matters. So thank you all for that. As has been mentioned, Praveen Karki and Pratima Srestha from World Bank, and of course, Professor Vishnu Pandey from Trinivan University deserve a lot of thanks for this, particularly Vishnuji. I think you have been behind this for quite a long time. And I would also like to thank a few of my own colleagues at ECMOD, Neera Sresthapradan, who could not make it today for this closing, Sunita Chaudhary, Shivang, and Sharmila for many different supports in organizing and conducting this training. So with that, I would like to thank everyone else who I could not, name in particular, but deserve thanking, and everyone else. So hopefully, this will be something very useful. Let's look forward for its use, and also another opportunity to meet you all, hopefully in person. Thank you very much. Back to you, Vishnuji.
Thank you so much. And with this, we conclude this session. Like mentioned, I think in the opening session also, and also indicated by Arun sir, we will be probably having the second episode sometime in November. We are yet to finalize the dates. They are particularly for those who could not attend this session because of the various limitation. We'll be providing opportunity for them. But those who are attended this session and want to learn more and have some confusions, they also would have opportunity to participate. In that case, they have to let us know once we announce the training. Thank you. Have a good time to everyone.
Thank you.
Thank you very much.
Thank you very much.
Bye-bye.
Bye-bye.
Thank
See
you.
you.
Bye-bye.
So much.
Thank you very much. Thanks a lot.